Nate said, I'm Daniel Verkamp. I work at Intel on the Storage Performance Development Kit. So we're going to talk about a whole bunch of stuff here. A lot about how the building blocks of SPDK fit together. So first off, we're going to talk about the threading model that we like to use. It's not the only possible way to build software, but we're going to talk about why we chose the way we did for SPDK. We're going to talk about the environment abstraction layer, which lets you plug in your own DPDK-like abstraction layer. We're going to cover the application framework, which we use in our example applications like the iSCSI target and the MEME over Fabrics target. And we're going to talk about the block device layer, which provides an abstraction over all the different block device drivers we have. And then if we have some time, we'll go through a few walkthroughs of how we use these tools in our example applications. So the idea here is that we have this modern hardware with lots of cores and lots of I/O queues. So we want to design our software to take advantage of these ideas. Right? We want to be able to design with that hardware in mind. And we also want to take into account modern CPU performance when we do things like context switching and interrupt handling. So the OS gives you the ability to do multitasking on a single core, right? Switch between different tasks, different threads. And it was really important when you only had one core or maybe two. But over the last 10 years or so, we've started to build CPUs with many more cores. So maybe we want to take advantage of that and achieve high performance by dedicating some of those cores to specific tasks. You couldn't do this when you had one core, right? But maybe, like for example, in the vhost case that we talked about this morning, you can dedicate one core to doing vhost storage processing and actually get efficiency benefits over the whole system by doing that. And we also want to avoid interrupt handler overhead. So on a busy system doing I/O all the time, the interrupt handler itself is actually pure overhead. It's not doing any useful work. So if you just do a polling model, there will almost always be something to do when you poll. So there's not a waste. And finally, instead of using locks to achieve concurrency between threads, we want to pass messages so that we can avoid stopping the thread that's doing work and building our asynchronous programming model. So the idea here is that we're going to talk about some existing threading models and then what SPDK provides. The most basic idea here is one connection per thread. So maybe you're building a storage server or a web server, any kind of high concurrency application. If you have one connection per thread, you have a really easy programming model, right? You say read or receive or write, and it blocks until the data is ready. And that's very straightforward. You can write single straight line code. But it means that you have a lot of overhead in terms of memory and context switching and interrupts, right? Because each thread is only servicing one connection, and as soon as you block, now you need to switch over to another thread and throw away your entire TLB and all the other issues to do with context switching. So one example of that would be the traditional Apache worker NPM. Oh, I'm sorry. Second idea is let the OS multiplex some of these events onto a single thread. So we have abstractions like select or poll or epoll. And we let the OS tell us when one of those things is ready. And this is a big improvement in terms of overhead in memory because we need fewer threads. We can just multiplex all of the events onto one thread. But we still have that interrupt-driven model where we're wasting time waiting for the interrupt handler to run. And it's also not an efficient model to build polling. So these epoll type APIs, even though they're better than select, they're not the most efficient way to poll devices. But this is used in lots of software all over the place. Apache, NPM, the Nginx web server, and so on. So the third model on the list here is the SPDK model. We want to use asynchronous I/O with polling. So asynchronous and event-driven sound very similar, but what we mean by it is that you submit an I/O, and then at some point later you check to see if it's done. And there's no automatic interrupt-driven response to that I/O completion. So this is the same idea as the previous bullet. We reduce memory overhead by having fewer threads. We don't need interrupt handling because we're doing polling, and we don't need to context switch because we're handling concurrency ourselves. The only downside here is that it's more complicated. You need to think about asynchronous handling yourself and manage the concurrency between tasks within your program. So we have some tools that help with that. That's what the rest of this talk will be about.
So Daniel, I have a question. Can you guys turn it on?
Microphone's not live.
Yeah.
Okay.
My question is, so for all of these other programming models, you have other examples, surely there must be something besides SPDK that uses the SPDK model.
There is, and don't call me Shirley. So this is exactly the model of an embedded programming system, right? You're in charge, you take over the hardware, there's no OS in the way, right? DPDK uses this exact model, right? You want to remove as much of the OS overhead from the processing path as possible and just run useful code, if you like.
Thank you.
Any other questions on that slide before we go on? Okay. So, like we just said, we're targeting this asynchronous and polled model. So we're going to talk about how we build software that provides that model. The first thing up is the environment abstraction layer. So the idea here is that we need a few different pieces of functionality to build that software, but we want to provide those in a generic way that's swappable, and we want to make it flexible for the user. So what exactly am I talking about here? We need memory allocation, and it specifically needs to be memory that can be used for DMA, because we're writing user space drivers that are doing DMA directly to memory, like zero copy, and it can't be being swapped out or moved around while we're DMAing to it. We need PCI device access, so we need to be able to map the base address register and access device registers. We need to do thread startup in a generic way that allows us to pin those threads to cores for performance reasons. And we need a few data structures. So we need a lock-free ring and a memory pool that can be used for multiple threads. So this may sound familiar. This is all built around DPDK. So we initially used DPDK directly, but we now have a configurable environment abstraction layer that puts a really thin layer in between us and DPDK. And you can provide your own here if you don't want to use DPDK. So there's an interface, env.h, which defines those functions you need to produce to implement your own abstraction layer, and it's configurable with a configure switch. So the idea here is just that it's flexible, and you can choose to not use DPDK if you don't want to, but we provide this DPDK default implementation.
I've got another question.
Okay.
My question is, so if SPDK and DPDK kind of came along together, does the SPDK team drive any changes or fixes and things upstream, so to speak, back to DPDK?
We do, in fact. So yeah, we're working at this flexibility angle from two directions. One is we're allowing you to replace DPDK with something else entirely, but several of the patches in recent DPDK versions have been from Ben, for example, working on improving the way that memory mapping works and making DPDK integrate better into other applications. So the DPDK programming model is very similar to ours in that it sort of wants to own the machine and it thinks that it is the center of the world, right? But we can improve that by making it less, it fit better into existing programs like our RocksDB integration that we talked about earlier. So that was the environment abstraction layer that provides really low-level operating system functions. Now we're going to talk about the application framework. And this is another layer above the environment layer that lets us put together all these asynchronous I/O components. So we have, for example, the polled mode NVMe driver and the blob store and the NVMe over Fabrics target, and we want to put these pieces together in a way that we can actually run like a real program that we can actually benchmark and show how it works. So we have the example application framework, and it glues together these components. So it builds on top of that environment abstraction layer, those basic memory allocation, and PCI device access functions. And it lets you glue together these other components, and it's example, really. So if it works for your use case, that's great, but it's also really just a way to show you how to put these together, how we think about the components. So there's really two kinds of things in SPDK. The libraries, which is the main sort of deliverable, right? We want to have reusable components that are usable separately and not depending on each other necessarily. And then we have applications that are examples of how to put those together. And we're really targeting all these libraries to be totally separate pieces that you can pick up and use by yourself. So the application framework is definitely used in all the applications in app. It's also currently used in some places in the libraries because it was convenient and because it was sort of put into library form after the fact. But the long-term goal here is to provide provide libraries that are separately usable. So we're going to talk about four different things, four components of the application framework. Reactor, the polar, the event, and the I/O channel. These are the building blocks for asynchronous applications.
Young man.
Yes, sir.
It seems to me that all of these things. Yeah, it's still me, guys. These things all look very much like design patterns.
That's exactly right.
Yeah.
So the reactor is an implementation of the reactor design pattern. It's responding to events in order. And the polar and event are also essentially just implementations of ideas that have been around for a long time, patterns that other people have come up with. So let's talk about the reactor. This is essentially an event loop. So if you don't like reactor pattern or design patterns, just think of it as a scheduler or an event loop. You choose at startup time how many cores, how many CPU cores you want to use, and the reactor runs on each one of those cores, separate reactors individually running. And they're pinned for various reasons, mostly because we want to be in control over where our code runs for new locality reasons and performance reasons. So it has two jobs. Most importantly, it polls I/O devices. So this is the bottom half of the asynchronous programming model. We send I/Os to these I/O devices, and we need to somehow know when those asynchronous operations have finished. So each reactor can have several pollers running on it, looking at different I/O devices. The second job is to poll the incoming event ring. So this is a cross-thread communication mechanism. Each reactor can send events to any other reactor. And those reactors are constantly polling for incoming events to pick those up.
Okay, another question. So if the reactors are polling the event loops and they're polling the polars, do the reactors make any decisions for themselves, or are they just looking for actions?
So yeah, the reactor is essentially just a container for these two concepts, right? It's really just a loop that's constantly running each available event and each available polar. And essentially it's a multitasking system, right? We want to run each of these in one after the other. So we're going to talk about polars first. Let's zoom in here on one specific polar. So the idea here is that someone somewhere schedules these polars to run on a specific reactor and tells them what to do when they run. So a polar will look for completions on maybe one NVMe hardware I/O queue. And it runs as many times as possible on the reactor, which is the reactor's job to schedule those. You can also decide to run them less frequently if you have some lower priority tasks. You can add a timer to it so that it doesn't run every possible time around the loop. So let's walk through here. What is this actually doing? Somewhere someone is submitting an I/O, and on this NVMe device, let's say down here at the bottom, has a hardware submission queue. So we submit the I/O to the device. The device is going to go off and process that I/O. So our submission path will return and go do something else. And then later, the I/O will complete and will be submitted through the completion queue back up to our host code. And at some point, a poller will run on this reactor, which is scheduled ahead of time, and we'll check that completion queue. When it picks up that completion, it will call an I/O completion callback that was configured when you submitted the I/O. So that I/O completion callback will run, and will finish and return back to the caller, which is the reactor, right? So it'll continue to run other pollers and other events.
So just to clarify, the thing that submitted the I/O there was the reactor.
Well, so the code that's submitting the I/O could be another poller or the result of an event. It doesn't really have to be running on a reactor per se, but you configure essentially at startup time which pollers are checking which completion queues. So that's the association here. The completion queue is associated with a submission queue, which you submitted the I/O on. This could be any kind of hardware I/O device that's asynchronous, right? So this could be NVMe, it could be a network card, anything that takes some amount of time to do an I/O that we don't want to wait for. So that was the poller. So the poller can also send an event in that I/O completion callback, which is the next thing we're going to talk about. Oh yeah, go ahead.
So it looks like you need a one-to-one mapping between the poller and the I/O device, right? How do you know how many poller you need?
Well,
you discover it or dynamically deploy them? How many tasks, poller tasks?
Yeah, it's a good question. There's actually really, it's up to you, right? You get to decide, but there's typically one poller per I/O queue even. So modern NVMe devices can have lots of queues, and you probably want to use them on different reactors, different threads, so that those threads can run independently. So we're going to talk a little bit in the next few slides about the block device layer, which will automatically run pollers for NVMe, for example. But yeah, this is under your control. You register the pollers and decide what they will do. Like, it's just a wrapper for a function pointer with a specific task that it needs to run. And beyond that, it's up to you. But we'll talk about how the block dev layer uses pollers shortly. Okay. Oh, we got another question up here.
Is there a mechanism that you guys are thinking about, like, for example, go ahead and allocate X number of pollers, and based on the need, can we enable those pollers?
Well, not really. So they're dynamically addable and removable. So at any point, you can decide that you no longer need a poller, but it's really just a sort of task that you want to run on a reactor. So when you start up and you want to use a specific NVMe device, you would schedule a poller for each thread that's using that, right, each core, so that they'll check for completions on their queue. They're not like a reusable, right? You can just schedule them whenever you need them and then turn them off later when you don't need them anymore. So it's not like there's a fixed number of them that you can use. They're just dynamically allocated whenever you need them. So let's talk about events. This is the inner core communication mechanism we talked about. So this picture here is, let's say reactor A is running on its own thread and wants to communicate something to reactor B. So maybe you've got I/O processing handling on reactor A, and you want to pass off an I/O to be compressed or some other long operation to another reactor that's handling that. So we use these for cross-site communication, and we essentially pass a message with a function pointer and its arguments over to the other core and then run it.
One question here.
Yeah, go for it.
So you showed it previously in one of the diagrams, reactor can send events to other reactors.
Right.
Is it always initiated by pollers, or is it the reactor itself can send?
No, so this is the code that's running anywhere, really. It doesn't even have to be on a thread that's managed by a reactor. So we'll talk about it real shortly here. The way this works is that the calling code drops a message onto a lock-free ring on the destination reactor. So you don't even need to be running on a reactor to send this message. You can be running on some other unrelated thread, as long as the destination is a reactor. Right?
No,
So
are there any specific cases where reactor itself can send the events?
no, so the reactors don't ever send messages themselves. These are just the user code, right? So you're writing your application that wants to communicate So maybe you want to process an I/O in a sort of a pipeline, and these steps of the pipeline are not all on one core. If they were on one core, you can just call the functions in sequence, right? You can call one on the same core without any thread safety problems. But when the event comes into play is when you want to use another core to do part of that pipeline, right? You want to pass off this I/O and send the event over to another core, and that core will pick it up and continue processing in a thread-safe way, right? Because only one reactor owns that I/O at a time.
Thanks.
So we're seeing here in the picture that one piece of code, maybe a polar that picked up a completion, is going to send an event over to reactor B. So reactor A allocates the event off of a memory pool, and it fills out that function pointer that it wants it to run. And then it drops it into this multi-producer, single-consumer lock-free ring. So in the DPDK case, this is RTE ring. And that's no locks, right? It's an efficient operation. You don't have to wait. And then at some point, when reactor B is done running other polars or other events, it'll come back around and pick up this new event, pull it off the ring, and execute that function, and then free the structure. So it's just a single function pointer that runs to completion and then returns. And then at that point, it's freed. So that's really just a mechanism for sending events or sending a message over to another thread, right, and coordinating that way. Does that all make sense? Any questions? I think we have a question over here.
Are there any plans to combine with C++ futures and promises?
Well, so that's exactly what this is building up to, right? We don't have any of those fancy features in C. All the SPDK libraries are written in C, and that's mostly for, we want anybody to use it. We don't want to be tied to some specific C++ framework. So you could wrap a futures-like system around this. There's also other tools available like C-Star is an asynchronous programming framework that's written in C++. That's exactly what you're talking about. It's not built on SPDK, but you could wrap those ideas around these basic concurrency primitives. So unfortunately, C doesn't have closures, for example, so you can't really build that system in plain C, right? You have to sort of build it from scratch yourself. The question was, can you emulate that with set jump and long jump? I mean, you sort of can, but you don't get the continuation closure passing sort of features that you really need. Like, it's not a language feature. So in theory, you probably could. I think it turns out the code is probably simpler if you just do it explicitly. That's what we found in SPDK, at least. And you're welcome to do your own thing, of course. So this is just the example of how to put together the components. You're welcome to build your own much better abstraction framework if you have fancier languages or fancier tools available. So the last component here is the I/O channel. So we have NVMe devices that provide lots of queues, and we want to be able to use those in our software. And we want to be able to use them explicitly. So we want to say this thread gets an I/O queue all to itself so that nobody else uses it. And you can acquire it in a sort of block-free way, right? You don't need to manage concurrency around it because you just assign it to a thread. So I/O channel extends that idea up through the software stack. You can register I/O devices with the SPDK framework. And when you register a device, you tell it what to do when a user asks you to create an I/O channel. So typically you'll create one I/O channel per device, per thread. So let's say you have 5 different NVMe devices and you want to use them all on 3 different threads, you would create 15 total I/O channels, right? And each one would be for a specific I/O device on that thread. And when you did that, that I/O device was registered with the NVMe layer, which would say, when I create an I/O channel, I want to schedule a polar so that a polar will be running on your core to pick up completions for your I/O device for that channel.
Quick question. So if the I/O channel abstracts hardware I/O queues, right, and the BDEV abstracts the actual block device, does that mean you're pretty much wrapping any I/O device in some level of abstraction?
Yeah, I mean, it's a very thin abstraction, and it's not really involved in the I/O path, right? You're really just setting up the polars to pick up completions. But you pass that I/O channel along when you submit an I/O, right? So yes, it's an abstraction over multiple kinds of hardware devices with queues, and that's pretty much, it's used throughout SPDK. It's really integrated into all of our layers of our stack. For example, the block dev layer that we're going to talk about shortly uses it to do this polar registration so that you don't have to think about it at the application layer. You just have to say, I need an I/O channel for this thread. So we use this all over the place, and it's actually not part of the application framework. It's really a separate concept because you can even use it if you're not using our event library, right? Our concurrency mechanism. So now we're going to talk about the block dev layer, which is an abstraction over block device drivers. And we want to be able to use specifically our NVMe driver, but in theory some other ideas, other hardware access mechanisms too, in a consistent way without knowing whether it's an NVMe device or a SAS device or whatever. And the block dev layer provides asynchronous I/O in a generic way. That's the big idea. We have read, write, flush, and trim, right? Those are the main block operations that we want to provide. And you don't need to know when you're calling it which kind of device you're talking to. We have scatter gather list support, so this is the vectored I/O type of functions. You can provide an IOV. This requires the backend to support it, of course, so if you have an NVMe device with scatter gather support, you get it all the way up through the block dev stack. And it integrates with I/O channels that we just talked about to schedule polars and register them. The other big thing that we provide is the ability to layer on top of these hardware devices with a virtual block dev. We're going to talk about what that means in a minute, but that's where you would want to implement sort of storage service functionality. So we've got a few different BDEV drivers. The big one is NVMe. So you can access local PCIe-based NVMe devices, and you can access remote NVMe devices over NVMe over fabrics through the block dev layer. You can access malloc devices, which is our sort of test RAM disk block dev. This actually has an integration with our copy engine framework, which hooks up to the IOAT DMA driver, which allows you to do copy offload, essentially. So when you submit an I/O, you could use a regular memcopy to copy the I/O back. But in our case, we also provide you the ability to use the DMA engine to do the copy asynchronously. This is mostly just for testing, but it's an interesting performance benchmark to say, how does my device compare to sort of the speed of light? We have a block dev that integrates with the Linux libaio library, which is the best way to do asynchronous I/O to kernel block devices. So this is not as efficient as a real complete user space driver like our NVMe driver, but if you want to access something that doesn't have an a user space driver already written, you can still get to it using this AIO functionality. And we talked about this morning a little bit, we have an RBD wrapper, so we can access Ceph devices as block devices through the Rados block protocol.
I'm super curious. So if you support RAM disks through the BDEV, does that mean SPDK supports persistent memory and so on?
Not per se. So the malloc RAM disk driver actually calls the environment abstraction layer allocation function to get its memory. So unless that returns the memory from the NVDIMMs, it's not going to actually use NVDIMMs. But we do have the idea that in the future we could add support for the PMEM libraries, which provides an abstraction over non-volatile memory programming models. That's not in place right now, but that would be certainly something we would like to do. So now let's talk about that virtual block dev thing, layering block devs. So the virtual block dev is a driver like the other BDEV drivers we just talked about, but instead of accessing a real hardware I/O device, it can claim underlying base BDEVs and then perform some function like a storage service and then expose another BDEV out the top. So you can do all sorts of storage services here. You can do RAID, you can do dedupe, caching, anything that you could take blocks in and then produce blocks out. We have an example of this, which is a really simple split block dev, which just takes an underlying device and slices it up into equally sized pieces. You can see how that would expand really easily into something like a partition block dev. And you can obviously claim multiple block devices per virtual BDEV and perform RAID type functionality across them. This is pretty new territory. We got this simple example here, but we'd like to have community input on what this layer should do and how it should fit so that we can allow you to plug in your own features in there.
Now, what if I wanted to take multiple different kinds of BDEVs and stick them under one virtual BDEV? Like, for instance, some of your Linux AIO and an NVMe BDEV.
Yes.
Is that possible?
Yeah, so this virtual BDEV interacts with the other BDEVs through the BDEV abstraction, right? So it doesn't really need to know what kind they are either. And you could definitely build something like a caching or tiering layer that would take 2 or more block devices and decide which one to write to. And it doesn't even need to necessarily expose the same set of blocks as the underlying devices, right? You get to choose what to do in the I/O processing in the read and write paths. And as we talked about this morning, the blob store is essentially a block allocator. We want to make this into a BDEV that you can use to provision a single large block device into smaller ones. That's not done yet, but that's on our roadmap. So those are all the components.
Hey,
that
Danny, we got a question up
Oh
here.
yeah, go for it.
So the idea is from the block dev to virtual block dev, getting all the any enhancement features like RAID and other things, or how does the design being put together there in between? For example, if you want to put in a security or encryption or whatever it is, so is that the layer which is sitting in between the virtual block dev and the block dev?
Right. So the idea is that, well, we'll talk about the example apps here just shortly, but let's say you have your iSCSI target and you want to provide an encryption layer that works on all the block devs, regardless of whether they're NVMe or whatever. You could absolutely build that as a virtual block dev. And then the app layer would look at that virtual block dev instead of the underlying block devs. So yeah, crypto, like block encryption would be absolutely something you could put in the virtual block dev. Yeah, we're going to talk through how, well, so it doesn't actually use the virtual block dev layer. We can talk about it more offline though if you have questions. So we're going to talk about how the NVMe over Fabrics target works and how it uses the application framework and the BDEV layer. So 2 steps to this process. We're going to first talk about how a new connection is accepted and set up on a core. So at the bottom of the picture there, you can see the connection. Connection comes in over the network, the new connection request. And there's an acceptor poller running at startup that will continuously look for new connections. And it will decide where to schedule that connection, essentially. So let's say we've pre-configured it to know that this connection will run on reactor 1. So we pass that connection request over to the destination reactor using an event, right? So that event was passed through the lock-free ring on a reactor 1 and then arrives. The reactor 1 will pick up that event, and the event itself will actually schedule a new poller. So this particular acceptor event that we set up will run a function that creates a new poller to handle that connection. So now that poller is running over on that other core, looking at a new connection that we've created. We're going to handle an I/O on that connection. So the new connection poller will pick up an I/O off the network queue. It'll send it down to the underlying storage device at some point. So this is asynchronous storage device, of course, and we'll have a new poller that handles that storage device on that thread. It'll pick up the completion when it finishes and send it back out over the network. So the whole process here, as you saw, was driven by the pollers. Like they're picking up these asynchronous completions and triggering the next step.
So quickly, in this diagram, it looks like somehow that reactor 0 or thread 0 owns the network. Is that the case?
Not really. So the acceptor polar will have the initial socket that's in listen mode, essentially, right? So you're accepting new connections there. But when we get a new connection, we'll call, this is RDMA, so it's a little bit different, but the same idea as a socket programming model where you would call listen and then accept, and accept will create a new connection that we pass off to the second reactor. And those two connections are totally independent. They're not, it's using the same network device, but they're separate connections in terms of resources, and you can use them independently. Good question.
So in your example, are the connection and the storage polars scheduled on the same reactor? Or
Yeah, they are. So, if you look at the code for the reactor, it's very simple. All it does is look for the next polar in line to run and run it until it completes, and then look for events and see if there's any events. So when you schedule two or more polars on a reactor, they're just added to a list, and we run them sort of round robin. And each one will run in turn and check for its completion. So these are both running on the same core, but they're never running concurrently. That's the big idea here, is that these polar functions don't need to know about concurrency. They just need to know that that connection is only being handled on that core, so nobody else will be touching your data. You don't need to take locks. And the only time you need to care about concurrency is when you want to interact with another core or another connection, for example. And that's when you would use an event to pass over to the other core.
And just a follow-up question, how do you decide where to schedule it? Like if you have a polar, how do you decide which reactor to schedule it on?
Yeah, that's a good question. You can do whatever you want here. This is tools for the user, but in our example applications, for example, the NVMe over Fabrics target, you specify where the subsystems are running at startup. So you can say, this subsystem is attached to this NVMe device and this network interface, and it's running on core 1. And maybe a different one is on a different core. So this is totally flexible in the programming model. You can choose to do whatever you want there, and maybe that's where a lot of the smartness or value add comes from. But in our example programs, it's all just statically configured when you start the subsystem. Yeah, so locality, exactly. That's why we really want to be able to
Can you just repeat the question?
Yeah, the question was, this is for, you need to handle locality and you know about, I assume you mean like NUMA and stuff like that, right? So we're going to have a whole talk about benchmarking and some of these NUMA pitfalls tomorrow, but that's exactly why we want to be able to schedule these things on specific cores, right? You want to say, I know that this network adapter and this NVMe device are on NUMA node 1, so I'll run my polar on a core on that NUMA node.
So question here.
Go for
A
it.
question here.
Yeah, go for it.
So in case of NVMe or Fabrics example, NVMe Fabrics also has IOQs and whatnot.
Right.
How do you bind different IOQs to different reactors? Is it possible?
Well, so this is, it gets confusing because you have these network queues, which are sort of one-to-one mapped with IO queues at the Fabrics layer, but you also have a queue to the underlying storage device, which is also sometimes NVMe, right? So the general idea here is that you don't share a specific queue between cores. You can if you want to, but then you need something like locking, right? You need to have mutual exclusion. So in the SPDK applications, that's what the IO channel allows you to do, is allocate individual queues for each core separately. And
So that's what I was going to say. Your slide's confusing because you've got your cores both accessing the network. What really happens is you're using the RDMA library
Right.
to create a separate queue pair.
exactly, yeah. The
Right.
arrows,
So really, that network box should appear in two places.
Right.
And
Yeah.
so you actually have core thread isolation there, but that picture is a little bit confusing.
yeah, I'll blame Jonathan for that. But
My fault, guys.
I think I made that picture actually, but exactly. Those two arrows are separate queues, and they can be used totally independently. It's one underlying network device, but yeah, networking is a little bit different, right? You have the same physical shared fabric, but the connections are independent, and the hardware knows how to send them to the right queue.
I will mention that there is a incredibly good deep dive into NVMe for Fabrics tomorrow morning. So if this is a topic of interest, come back.
Yeah, we'll fix our pictures.
So,
Yeah.
so assigning polars to the reactors, so that gives a lot of flexibility, but also to squeeze out the maximum performance. Do we have to do trial and error to figure out what works the best? And this is this configurable at runtime, or do we have to?
Yeah. So the first part of the question is just, is it trial and error? I mean, partially, you can use your intuition or use your, the things you know about the hardware to figure out ahead of time what you should do. But definitely there's some amount of, how fast does this go? How many NVMe devices can I pull on a single core before I run out of steam? That's some of what the benchmarking stuff is about. But some science and some trial and error, certainly. And is it configurable at runtime? Yes. So the reactor mask, which reactors, which cores you want to use, is currently set up at startup. So any core that you ever want to use during the run of the program, you have to know at startup. That's mostly because that's the way DPDK works. There's no hard and fast reason that you couldn't add or remove cores dynamically, because it's really just calling OS thread functions underneath and pinning them to specific cores. So if that's an area that you would need flexibility in the future, we could look into that. The other part of it is that these reactors have the ability to, you can configure a sort of acceptable latency. So if you decide that you can wait up to X number of microseconds for a specific event, you can configure them that way, and then they'll go to sleep if there's nothing to do. So there's essentially almost no cost to having extra reactors if they're configured that way, right? They can just be sleeping in the OS sleep function. We can definitely look into ways to allow you to manipulate that at runtime. All of the polar and reactor stuff is totally configurable at runtime. Like, you can add and remove polars dynamically whenever you want to. There's another question over here.
So in this model, does the network polar and the acceptor polar share the same core? Sorry, continuing on the same question.
Sure. No, well, so yeah, the dotted line here is sort of dividing between CPU cores. The acceptor polar is running on some core looking for new connections, and maybe that's one that would be scheduled with a timer because maybe you don't care. It's absolute latency for new connections is not super important, but the connection polar will get scheduled on a different core, perhaps. It could be the same core, but in this picture, they're on two different cores, right? They're independently accessing the network device.
So the processing of a storage polar doesn't stop the connection polar from receiving further requests?
Well, so it does in the sense that the polar functions are just run from start to finish, but they're designed in such a way that they check for completions and then they return. So the storage polar, for example, if it's an NVMe device, would call NVMe process IO completions, which will look at the queue, the completion queue, and if there's no outstanding IOs, it'll just return right away. So then you can run the next polar again. So you'll just bounce back and forth between connection polar, storage polar, or however many are scheduled. But you have to definitely keep it in mind so that you don't just sit there and block, right? You don't want to block in a polar because then no other polars will run. I think we got a connection back, question. So do the polars process multiple IOs at a time? That's totally up to you. In the case of the NVMe one, for example, we provide a parameter that says how many IOs to do in a batch at most. So you can totally do either one, right? If you want to, it's mostly a question of fairness, or if you want to spend a lot of time finishing IOs for one device, then you're not looking for completions for any other devices while that's happening on that core. So you can totally do batches though, and it makes sense for locality reasons to do that. I think we got it. There's another one over here.
What kind of framework, what kind of environmental abstraction is provided to guarantee cache coherency at like level 3 or even level 4 caches to allow for event communication a little bit more efficiently when you know that you're going to have cross-core communication more often between reactors versus reactors that may not communicate as much?
Yeah, well, so what we use here for these rings in this picture is the RTE ring data structure, and they use x86 atomic instructions to make sure that access. Yeah, they are expensive. So, and these are multi-producer rings, right? Because any reactor could be writing into that ring. In theory, you could design a system where you have a one-to-one, queue for each possible source and destination, but that gets out of hand pretty quickly if you have more than a few cores. So this is sort of the best possible option without allocating huge amounts of memory. So, I mean, the answer to the question is we use the CPU atomics to ensure coherency, and that's, there's no way around that for cross-thread communication, right? You just have to have some point where they contend. Yeah, go for it.
So on the NVMe storage side, we have this submission queues and completion queues, right? Meaning you can process like X number of commands. Did you run into any throttling issues where application is issuing requests and you have like X number of requests that you can send it to the backend, and how do you handle that?
Yeah, so we could talk more about how the NVMe over Fabrics target works offline if you want to, but there is queuing in software if you need it. Like you can keep requests if there's not enough hardware queue depth in some software queue and resubmit them. You can trigger that on the completion of a previous IO, right? Because when you pick up a completion in the polar, you'll know that there's a free slot to submit a new IO. And some of that is handled inside the NVMe block dev layer, or inside the NVMe driver, really. But you can do your own queuing if you need to expose more queue depth for whatever reason.
Yeah, so I think you give a great example here. You want to using the SPDK integrate with NVMe over Fabric, right? It's so all this the polar thing is because of SPDK implementation, right? So there's a traditional way you can do the NVMe over Fabric. So I got it. You have a connection polar, acceptance polar. That's all the NVMe over Fabric driver layer. That kind of abstraction, but this is when you're doing the SPDK on top of the NVMe, right? And also on top of the NVMe, our Fabric layer. What about like the Fabric, the RDMA part? So that part doesn't take SPDK, right? How do you integrate? So are you gonna integrate with DPDK? Say if I running RDMA with DPDK, right? You need to provide all this service to make it like a queuing, mapping. How do you work it? I mean, how do you?
Yeah. So, I mean, today what we have in the NVMe over Fabrics target, the RDMA support is provided through libIbverbs, which is the InfiniBand verbs programming interface. And that is, it provides essentially a polling model that we can use. So it's not 100% designed to match up with the SPDK programming model, but we can integrate it into our pollers, right? We can check for completions. And in theory, you could write your own full user space network driver. Maybe DPDK provides those for RDMA, I'm not sure. But even without that, right, you can integrate with existing network stacks using our pollers as long as you can check for completions and return without waiting.
Yeah, if that's the case, you wanna like running network stack in the non-polar mode, right? I mean, you're using the interrupt-driven context switching, and other thing you're using the polar thing, the more efficient asynchronous I/O. There's some kind of mismatching,
Yeah, I mean, you can certainly improve that if you have a fully user space network stack. That would be optimal, right? You can fit it right into this model. But even if you don't, we integrate with the kernel networking stack for iSCSI and the IBverb stack for RDMA over Fabrics. I mean, it's not the end of the world, right? There's always levels of improvement over what we have right now, but it works. Another question over here.
So if I want a backend task, like a task, should I have a timer in the reactor itself, or I should have created a separate reactor for handling all the timer processings?
Well, so I can talk about, I'm not sure you mean the polar with timer?
The polar with the timer.
Yeah, so I mean, the reactor handles that. Today that's a very simplistic implementation. So we have one queue of polars that runs round robin with no timer. And then we have a different set of, a list essentially of all the polars that have timers configured. And each time that we run around this event loop, we check if the most, next up timer is expired, and then run it. So, and then requeue it back into the place where it will expire next. So that's a really simple model, and it's, a linked list and not the best optimal thing there. So if you want to do something efficient, there's like the RTE timer framework that uses a sort of timer wheel type of implementation. And if we needed that in SPDK, we can certainly build something more complicated, but this is for just trying to give it a little more fairness. You can tune how often you want to run a poller if it's not as important. It's maybe not, it's not guaranteed deadlines or anything like that. So you don't want to use it for something that's time critical. It's just more like this only needs to run every millisecond, or this needs to run every X microseconds.
So I have a question here. On this side.
Yeah, go for it.
So how hard it is to actually replace the poller? Because let's say I have a long-running process or thread, which I don't want to relocate to another core. I prefer to just say run it locally on this reactor one. Then I can actually do my own yield.
Right.
Then, but I still want the poller to be, say, responsive enough.
Yeah, you have a few options there. Number one is that this whole thing, the application framework, is for the examples, right? If you're building your own application, you can build it with your own concurrency model and not use the reactors and pollers at all if you don't want to. As far as integrating it with something like coroutines, I'm not sure. It would probably be possible, but you just want to ensure that you don't spend, a lot of time in a single function on that core, because it's never, in the SPDK code, it's never going to yield, right? It's going to continue running until you tell it to stop. All good? Okay. So the other example we have is the vhost target. So we talked about vhost this morning. This is a VM virtualization mechanism for I/O. It looks a lot like the NVMe over Fabrics target. We're going to skip the whole setup steps that we did for the connection in the previous one and just assume that this reactor is checking for events on this specific queue. So the VM sends the I/O over to our target. This is over a shared memory queue for vhost. We check that queue using a poller, which means we don't need that interrupt VM exit, right? In the normal vhost case, there would be a sort of kick from the VM or the host into the target. We're skipping that because we have a poller. We pass that I/O off to the SCSI layer, which is a generic part of our iSCSI target that's gotten repurposed for vhost. The I/O gets submitted down to the backend storage device, which is a BDEV. And that BDEV poller will pick up the I/O when it's finished, send it back to SCSI. And then here we have a little bit of a tricky corner case, is that we send an I/O back to our own reactor through an event. So this is really leftovers from iSCSI, where we sometimes had configurations where you needed to send an I/O to a specific core handling that SCSI device, and then send the completion back across the core to a different core. So it's totally possible to submit an event back to yourself, and the reactor will pick it up later. Then we send that completion back over the vert queue and back to the VM. So this is pretty similar to the other model. It's the same idea. The pollers are picking up all the completions and triggering the next step. Any questions on that one?
No, but that is a beautiful chart.
I think you mostly made that one.
Hold on, we got a question up here.
Yeah.
I'm just wondering, what's the mechanics or mechanism for figuring out when you're setting up a poller, or how do you decide what it sends the completion to?
Well, yeah, so I wasn't very specific in the slide, but all the poller is, when you register a poller, you tell it which core it's running on, and then a function. So it's just a function pointer and a parameter, and so you can make it do whatever you want. The BDEV layer, for example, will automatically configure pollers that will check for completions for that particular BDEV driver, but it's flexible. You can put whatever you want in there. It's up to you. Right. It really is sort of like a poor man's continuation or closure in C, except the language doesn't provide the features that you need to really build that. So you have to manage lifetime of anything that you pass as the parameter there, right? You make sure that it doesn't get freed before you call that function. The context, yeah. So when you register a polar, you say, here's the function to run, and then it gets, I think, either 1 or 2 parameters that are just void pointers, and you can decide whatever you want.
Do you have a lot of context that you can get access to?
No, yeah, it's totally up to you to pass in any context that you need.
So the BDEV and VDEV that you talked about in the previous slides, is it part of the SCSI block?
Yeah,
In this model?
the BDEV. So the BDEV
BDEV.
layer, I mean, I didn't call it out explicitly in this picture, but when the SCSI layer submits an I/O, it's actually talking to the BDEV layer. There's a SCSI to BDEV translation, and the BDEV layer abstracts over, NVMe or whichever device you're talking to.
Oh, that's all abstracted there.
Yeah, so the SCSI layer works with any kind of BDEV, and then the BDEV layer provides those underlying, read and write type functions. So yeah, in theory, you could even put something else other than BDEV under SCSI if you wanted to. That SCSI to BDEV translation is just like at the bottom edge. So you could swap that out if you wanted to build a different sort of block dev abstraction.
Okay, cool.
All good? Okay. So that's pretty much it. We're going to call back to our keywords here. Efficiency. We want to design our software so that it takes advantage of the hardware. And we want to know how the hardware works and design around that. We want simplicity, which we can get by using these building blocks that SPDK is providing so that you don't have to write all of this sort of boilerplate code. And we want to provide flexibility, so we have all these pluggable modular layers that you can replace and use however you want in your applications. So that's it. I'm totally, we can answer more questions here, and you can talk to me offline whenever, if we have time after. Any more questions over overall big picture stuff?
Awesome. Thank you, Daniel.
Thank you.